Okay, our first speaker is Yong who will be talking to us about KinkBB and formal verification.
Right. Hello. I hope everyone can hear me. Yes. Okay, great. So I really put up this talk as a demo talk, and the goal mainly is to just kind of give you a sense of how we've built a verified proof checker for, I guess, VeriPB, which you have been hearing about for yesterday, and I guess what you hear about later today, right? So I'm going to talk about some of the work that is probably highly related to the talk by Kiam yesterday on verified subgraph solving. So this is really part of the same paper, I would say. Okay, so I hope you can see when I kind of try to draw on the screen. So this is a demo talk. So I kind of want to go, I sort of have prepared a sort of a demo of how the verification works. As I said, it's mostly highly related to the proof logging talk yesterday. Please feel free to, I guess, interrupt me on Zoom if you need any clarification as I go through the stuff. Right. So the plan that I have for today is basically these 3 points. I'm going to kind of just quickly talk about ITP for those who haven't seen it or done some interactive proving before. And then I'll look at how we sort of built the KPB quote unquote backend, and then I'll quickly talk about the front end. And I'll explain why I say backend and front end in a bit. Right. So okay, Okay, so what is interactive theorem proving? And this is, I guess, hopefully there's quite a few people in the audience who already know what it is. But just quoting from this paper by Harrison, essentially it's going to be some kind of tool which allows us to humans to work interactively on a computer to produce some sort of formal proof. Okay. I'm sure many of us have heard, of ITP recently. That's because of Lean. But actually, ITP really goes back almost to the beginnings of computer science, and theorem proving, way back to the 60s and 70s. Okay. And one thing that's I would think interesting to note is that I guess traditionally there has been a lot of very important work in integrating automated reasoning tools into ITPs, right? So I guess one of my favorite tools, for example, is Sledgehammer, which really enables me to do proofs much more effectively using a theorem prover called Isabelle Hall. Okay, the way that these hammers work is, well, one of the ways in which they work is to have these ATPs produce proofs and then have those proofs be checked independently within the ITP itself as a way of getting the automation of the ATP without necessarily having to trust them within the ITP system. Okay. Now, for this talk and in this work, I'm going to be talking about verified proof checking, but there's a subtle difference between these 2 points in that here I'm going to be talking about verifying the proof checking tool itself, right, within an ITP. Okay, so hopefully the difference is somewhat clear in that this is kind of like a replay. Well, here I'm sort of verifying the tool as a whole. Okay, so the first thing I wanted to sort of demo is really how most ITPs work. Okay, so so here is my prover window. Okay. And here is my demo script. So I'm not sure whether it's big enough. If anyone can just shout if it's.
I think it's fine.
Okay. Okay, great. So generally, I mean, so I'm using a theorem prover called Hall4. There are a couple of other provers as well. But generally what happens in each of these provers is that you have some kind of user proof lying over here, right? And then we have the we're going to have the theorem prover sort of lying over here in this other window. And what happens is that I can interact with the prover by telling it that maybe I want to make a new definition. Like, for example, I'm going to send this definition over. Okay, I'm going to tell it I want to make a new definition. For example, here this definition that I just sent over was to, I guess, define how to interpret booleans as numbers, right? And the prover will tell me, well, it's accepted that definition, and so on. Okay. So I'll come back to this in a second. Okay, and of course, the main use of these ITPs is that we'll be able to carry out proofs. So, for example, so after processing some theorems, I could say that, okay, now I want to prove this theorem, which is a theorem about satisfiability. And sorry, there's a question in the chat. No, okay. Question about satisfiability, and then what I can do is interact with the prover by sending things, in this case, things called tactics, which allow me to sort of tell the prover that I want to advance the proof state, in this case, by, for example, expanding the definition of satisfies, and so on, right? So, right. So I hope the sort of interaction model is somewhat clear. I would say the high level model is pretty much the same for most provers, but of course some have much more polished interface than the one I'm using. Okay. So that's just a one slide view of ITP. Okay. Are there questions at this point? Yeah, yes. Hopefully not, because I can't really hear anyway. But if you have questions, please feel free to interrupt. Okay, so what is verified proof checking about? So I'm going to be talking about verified proof checking sort of for sub, which hopefully you've heard about yesterday. And I would say the general workflow kind of looks something like this. You have the some kind of untrusted graph solver, okay? And it has been set up so that it not only solves the input graph problem, but it also produces something, some kind of proof for that graph problem. And the workflow that we have for at least the VeryPB/CakePB interaction is that at the same time, we'll be able to feed this graph problem into a verified proof checker, and this proof kind of goes into CakePB. Sorry, I drew it a bit too fast. It goes into CakePB and comes out as a sort of a kernel or a simplified proof format that also goes into the verified proof checker. And together, the proof checker is able to then give a conclusion about, for example, whatever the graph solver decided about the input graph problem, right? So this gray box here is what I'm going to talk about, and it's basically all the verified. All of these steps have been formally verified. So we have a correctness theorem that's proved inside all four, which sort of states the correctness of this checking pipeline. So in particular, if it, for example, prints out a certain conclusion about the graph problem, then you can be pretty certain that the graph problem does indeed have those properties. Okay, so I actually want to skip this demo because I think Karen probably showed it already yesterday. Okay, so I'll just go on directly to the verification itself. Right. So now, I think one of the things that makes it interesting, makes VeryPB or the suitable improves a very interesting target for formal verification. I think it's really also closely related to the fact that it has been used in many it has been used to build proof checking pipelines for many combinatorial pipelines, right? So I'll say one thing is that, for example, verification of a proof checker is not that cheap. It's a pretty expensive task, right? And but what we have been able to do is to kind of build, because sort of many things are sort of depending only on very PB, right, emitting pseudo Boolean proofs, we were able to kind of build this common verified backend, right, which we called cake PB, which supports pseudo Boolean proofs. And then beyond that, right, we were able to build these things, which I'm going to call the front ends, right, which the main thing that we sort of do for each of these front ends is to just verify kind of this encoding step, right? And then by piecing together these two pieces, the front end and back end, we automatically get a proof checker for these various problems without kind of having to spend the effort of building the whole pipeline over again for each new front end, right? So I think this is a benefit that's really shared between using a common proof format for many different combinatorial paradigms. And well, one thing that sort of helps as well with this is that if so as we have been building this kind of cake PB backend, what we have found is that if we sort of optimize this backend in terms of sort of verifying new optimizations in terms of the proof checking, then automatically we kind of also improve the proof checking speed for all of those front ends as well. So there's this interesting back and forth relationship as well. Okay, so in the context of the proof checkers that I'm building, so I work within this broader project called Kiam, where it's essentially a programming language with formally verified, with a suite of tools for producing formally verified code. And in particular, one of the most important parts of this language is a formally verified compiler, which allows us to generate machine code, right? So when we use this together with proof checking, what that means is we are able to generate verified proof checkers, in particular where their correctness theorems have been verified down to the level of machine code. We have a guarantee that whatever machine code that you execute for this proof checker, if it, for example, prints that your input formula is unset, then it's really unset, and this guarantees at the level of again x86 or ARM and so on. Okay, so here's what I want to kind of demo, which is so how sort of this verification process works. Okay, so I haven't really sort of timed this properly, but hopefully we can do it in time. So basically I just have a sequence of, I think, around 10 steps as to how this verification goes about, but I'm not going through all of them, right? So first things first, in order to formally reason about anything, we're going to have to actually just erase this. We're going to actually have to start by defining, the semantics and syntax of, let's say, pseudo Boolean constraints. So here, for example, I have defined a simple format for a pseudo Boolean constraint, which is on the left-hand side, it's going to be a list of literals and coefficients, and we have a right-hand side. Okay, and what we have to do is to define what it means for a Boolean assignment to satisfy, what it means for a Boolean assignment W, omega, to satisfy this pseudo Boolean constraint. And we just say that, well, if you evaluate all the terms on the left-hand side and sum them up, right, in the assignment, then it must be greater than or equal to the right-hand side, right? So this is making logical definitions within the theorem prover, as I was going through just now. And we can make some standard definitions as well. For example, what does it mean to satisfy a pseudo Boolean formula, which in this case is interpreted as a set of pseudo Boolean constraints? Well, it's just saying that for every constraint that's inside the formula, it's satisfied by W, okay? And well, satisfiability and unsatisfiability, there are standard definitions, right? So this kind of gives us a base semantics in which we're going to prove things against for our proof checker. Okay, so the next step from there is to, well, I would say this is really like more or less proving some abstract properties about the semantics. For example, we need some lemmas, like, for example, if you insert a new constraint into the formula, into the set of formulas, the set of constraints that's already there, then well, it's satisfied by a constraint, sorry, by assignment W, if and only if W satisfies the original formula, and it also satisfies the newly inserted constraint, and so on. So these are all things that you could prove and state and prove inside the theorem prover. Okay, but also we can also prove some more abstract results related to
Yong Kiam.
Yeah, sorry, hello. Yeah.
Yes, can you hear me?
Yeah.
And these kind of simple things that you satisfy F
Mm.
and C if you satisfy F and you satisfy C.
Yeah.
Will the interactive theorem prover figure this out completely on its own, or do you need to help it in any way?
Well, I mean, it's basically just expanding certain definitions, right? And then you will figure it out. Yeah. So this is like the proof. It's 2 lines. So yeah.
So mostly it does it on its own, I guess. It looks like.
Yeah, more or less. Yeah. Yeah, these kinds of things are pretty simple.
Come up with these 2 lines.
Yeah.
Sorry?
You have to come up with these 2 lines, right? And you need the intuition that I mean, the fact that you have to do rewriting is pretty clear when it's pretty clear. The fact that Metis will work is not so obvious.
Yeah, sure. I mean, in Isabel, I think this would be auto, but yeah. I think I would consider this something that you'd be able to prove, like well, I mean, I think it's more difficult to figure out the statement than to figure out the proof, as I would say. Like, once you have the statement, the proof is not that difficult. Yeah, I guess. Yeah.
Could you show the dominance rule to prove all that?
No, I have of that, but it's on a separate script. So this file was just like I have condensed all the steps into one file. The dominance proof is, I think, let's see. Oh, so this is one part of the dominance rule. It's pretty long. So yeah, it keeps going until it's about like 500 lines, I think. Plus. Yeah. This is probably the full dominance result, roughly. Yeah. Because I mean, so in this kind of demo, I've skipped away things like the objective function, and other features of very PB, like call constraints and things like that. So yeah, if you want the full-fledged kind of thing, it gets a bit more complicated, and then the proof also becomes more complicated. Yeah.
And the handwritten proof in the paper is 3 or 4 pages, I think.
Mm-hmm.
So 500 lines isn't really that much.
Sure. Yeah. Well, but you should know that this is only for dominance itself. There's following from this, there's going to be also actually implementing the dominance check, which is more lines than that. And I'll give a small hint of how this like implementation side goes. So the thing to keep in mind is that I guess what I'm showing here is going to be more on what I'm showing right now. It's more on the abstract side of things, basically arguing for the correctness in terms of mathematics. And then there's still there's still actually a few steps before you can get something that is actually code that runs. And those 2 things are not necessarily the same. Yeah. Okay, but anyway, I should maybe move on, because I have like 800 lines in this file and 900 lines, and I have 7 minutes left. So yeah, so I guess similar to the dominance rule, actually, what we tend to do first is to kind of verify, for example, in this case, the cutting planes proofs system in a more abstract way first. So for example, in the cutting planes proof system, you can take a pseudo-Boolean constraint and multiply the left and right sides all by k, which is what this definition is doing. One thing to note is that this really looks like some kind of thing that you might write in a functional programming language. But in particular, you could write down a correctness theorem for this. So if the correctness theorem in this case is saying that, well, if I know that C is satisfied by a given Boolean assignment, then multiplying the constraint C by this coefficient K still the multiplied constraint is still satisfied by the same assignment, right? So, and I mean, the proof is essentially walking through, the mathematics, making sure that everything is, yeah. So it looks something like that. I mean, I've just copied this from the main file, actually. So yeah, so we would go about proving this for a couple of other operations, like for example, multiplication and addition. Addition is actually somewhat subtle because you actually want to add the two constraints together and make sure that they are still properly normalized. So the proof is a little bit longer, but at the end of the day, you prove something like that as well. So, if you know that omega satisfies both C1 and C2, then it will satisfy the addition of C1 and C2, according to our definition of what it means to add two constraints together. Okay, so that's this theorem. Okay, so just to recap, what we have done here in this step is to prove some abstract results, or I would say more mathematical mathematical results that we were going to be using in the proof checker. So again, going back to the dominance rule, this is where we would prove, for example, the argument behind dominance that does the induction on the decreasing sequence of with respect to the order, for example, right? So what's the next step? Well, the next step is to actually write down the proof checking algorithm that sort of uses these things. So here I've written down a sort of a very condensed format, which is, well, you're allowed to write a cutting planes step, which is, you can look up an ID, which is in your current constraint database. You can add together two cutting plane steps, or you can multiply one of them by a number. And then your top level proof is just, you can either, you can either write the cutting planes proof and store the derived constraint at a certain ID, or you can delete a certain ID, right? So it's a very sort of simplified proof system. And then, well, we can define, what it means to actually check the proof. For example, to check the cutting plane step, you do what each of them say, right? So if you see the proof tells you to look at ID n, then you look it up. If it tells you to add together to sort of the constraints derived from two sub cutting planes proofs, then you do that, and so on. Yeah, so one thing I guess if you're familiar with functional programming is that here I'm sort of using an option type to return, well, for example, if the lookup fails, then I'll return none, or otherwise I'll return the constraint that was derived. Okay, and then I can define, for example, the top level checking function, which is just running the steps as you'd expect. So if you have a cutting plane step, you check the cutting plane step, and if you successfully derive some constraint, you add it to your constraint database, and you increment for the ID counter by 1. If you are asked to delete a certain constraint, then you just delete it, keep the ID the same, right? So yeah, so these are all things that you would expect, and so if you want to check a list of proof steps, then you kind of just iterate this process over your constraint database and the proof. So this is all definitions, and what's interesting now is that, of course, you can prove the correctness of this checking algorithm, right? So you kind of want to say that, well, if my cutting planes proof successfully derives a constraint, then that constraint is implied by the original formula, okay? And that's expressed over here. And as before, you kind of do a big induction over the different kinds of cutting plane steps that you can have. And as the interactive prover basically tells you the kind of things that you need to prove. For example, you need to prove the case for looking at the ID, you need to prove the case for addition, you need to prove the case for multiplication, and so on. Okay. So I won't go through this proof, but I think I guess Matthias was asking, these proofs are somewhat straightforward. These are more or less just unfolding definitions and using the abstract lemmas that I've proved before. I guess the more subtle part about here would be if you're kind of putting in certain optimizations, like for example, in the redundancy or dominance rule, where you're allowed to skip certain proof goals, then you need to justify why you're skipping them. Or maybe in those proofs, when you have subproofs, how you're manipulating IDs and things like that, you need to be careful. For example, if you want your system to be actually satisfiability preserving, then you need to be careful about when IDs can shadow. So I haven't sort of really done that here. So for example, here, the top level checking kind of just allows you to delete any ID. And so what's proved here is that it's the proof system is satisfiability preserving in one direction. So it's not in the not the output formula is not satisfiability equivalent. Okay, so but again, you can actually prove a soundness theorem about this checker, right? And yeah. So yeah, I've written down the main points as to what we have done so far. We have formalized an abstract checking algorithm and the soundness for it. Okay, so in practice, the algorithm and the proof is a little bit more complicated than what's shown here. You have to have some kind of soundness invariant, for example, in dominance. Okay, and the point here, I would say, is more to keep details abstract and at the mathematical side. Okay, so I think I've actually run out of time. Can I take maybe 5 minutes extra? Or
Sure. I also have a question.
yeah.
What you've done so far.
Yeah.
Suppose I'm super excited about this and I want to do the same. Do I take a first 7.5 ECTS credits course on interactive theorem proving and I will be able to do this? Or how much, these magic lines, how much expertise do I need to realize, as Matthias said, that maybe just 2 lines, but I need the right ones? How hard is it to do what we've done so far? Is that a possible question to answer?
I would say, and I think Matthias can agree or disagree, is that if you have taken a standard course in interactive theorem proving, you should be able to do everything I've said so far, just without any difficulty, like a standard, I guess, intro course to Isabel or Lean or whatever. You should be able to do everything I've said so far, just fine. And yeah.
And with the after course, you will be able to understand it, and then it takes you a couple more months to be productive in the system.
Sure. Yeah.
You will understand it, and you will manage when you see it to work, and you will, in some cases, manage to work it yourself. But to be productive, you need to invest more time in it, I would say.
Sure. Yeah. What I was gonna say is that what I've said so far is kind of generic theorem proving. I would say, just define some things and prove things about them. The next part is actually where I would say you need a little bit more familiarity. In this case, familiarity with the KML code base. I guess in the case of Isabel or other theorem provers, you need to be familiar with whatever framework you're going to use to generate code. For example, the Isabel refinement framework or for LLVM. So I'll go through this quickly because I'm out of time. But really, the next step to do is to see if I ran this already. Oh, I did. So the next step really is to start generating code. And what's interesting with KML is that these definitions that I've written before, which are kind of functional programming like, right? What we can do is that we can automatically generate code inside KML, which is formally verified to have the same semantics essentially as those functional programs, right? That's what I'm doing here. I'm kind of translating what I've written in the theorem prover into something that can be executed. Okay. And I'll skip over this.
Inherent in terms of computational complexity. If you wrote an involved definition and the code is not so great, if you really polished your definition, you'll get nice code out of this.
That's a great question, because so for this you get essentially code that is more or less pure. So it doesn't use any imperative features like arrays, exceptions, and whatever. Okay. And actually what you asked about is the next point, which is yeah, so what happens if you actually want to have code that is, does things a little bit more efficiently? Well, at least for now, the way it's done by proof checkers is that you would have to actually write another copy of the code, which is optimized in the way you want. So in this demo, I actually rewrote the code, essentially parts of the code, so that, for example, it uses arrays. And once you start using things like arrays, which are sort of affect the state, then you need to use slightly more complex reasoning tools, which is why I also said like this part will require more expertise. Another thing that I do, for example, is to use exceptions in here, and that allows me to avoid things like boxing, which you would get if you're sort of passing results around in the option monad. So yeah, so I'm going to skip over these lines. These are more specific to the framework that you're using. But the main idea is that you would still be able to prove a refinement that essentially connects this code back to the proof system. Okay, and that's how you get a sort of a correctness guarantee. Okay, so I'll skip here. And I wanted to just say what steps are there. So what we have done so far, build the abstract mathematics, build the abstract proof system, build the concrete proof checker implementation, optimize it a little bit or a little bit more. And then, well, what happens next, which I'm not showing.
Another question, sorry for interrupting, but then you said like, so I take these definitions and there was a way to translate them into code. And then with the next step to be to prove on a function by function basic that this function one derived from the mathematical definition is equivalent to this thing that you coded up from scratch that is more efficient. Is this part of what is happening also, or?
Yeah, so the translation and this part about manually writing code, those two are, it's not like one step after another. Actually, it's actually it works hand in hand, in the sense that for certain parts of the proof checker, I'm going to use the translation. Okay, this allows me to kind of automatically get the correctness guarantee. And then for other parts of the proof checker, I'm going to handwrite it and prove it correct. And this part is more manual, but this allows me to write a little bit more efficient code. And of course, these two pieces of code, they can coexist, right? So typically what happens is I would only do the manual part when I actually need the performance. And then everything else I try to keep as much as possible within the pure part, which is automated. Does that make sense? So,
yes, so in principle, you can just generate code from the definitions from everything, then you run the proof checker, you profile it, you check which parts are too slow, and those you will optimize.
Yeah, essentially yes. But I mean, I would say in terms of the code that's optimized, there's a standard set of things that you do, and then afterwards, you profile, and then you see like, yeah, okay, these things have to be done better as well. Then you go back and fix those as well. Yeah. Okay, so anyway, so I'm skipping ahead here. So, well, what we do next is kind of produce a top level, sort of the thing that actually runs, the thing that I think Karen showed yesterday, which I'm not sure they showed, but we produce this top level source code in KML. Then you can actually compile the code into machine code, in this case using a formally verified compiler. Okay, and this allows us to produce a theorem down to the machine code, which I will skip showing here. Well, I do have it. I'll show it in a second. Okay. But going back to this, we don't just have, so everything I've talked about so far is just about building a backend, right? Which, as you can see, is quite a lot of work. But as I've said just now, what's nice about this is it allows us to actually build front ends as well. Okay, a front end is essentially an encoder that encodes a certain problem down into PB. So I have a short sort of example over here, which is actually for the click problem. So we can start from a mathematical definition of what it means for something to be a click. So this is pretty abstract, but for this definition, we can actually, for example, write down encoding of a problem. In this case, I'm going to encode sort of, whether there exists a clique of size k within a graph. Okay, this is a decision problem. Okay, and what you can do is, as before, you can actually prove something about this encoding. I hope this runs because I'm sort of halfway through the file, but yeah. So for example, this is a theorem that I could prove about the encoder. What it says is that, yeah, if assuming your input graph, the edges are symmetric, then you can show that, well, mathematically there exists a clique of size k if and only if your encoded set of constraints is satisfiable. Okay, and don't think
basically here you're proving you made a pseudo-Boolean encoding of the clique problem, the one that we would expect, and then you prove that there was a k clique in your graph if and only if this pseudo-Boolean formula had a satisfying assignment.
Yes, that's right.
I guess in the non-baby version, would you have a more precise statement that somehow line up cliques and assignments one-to-one, or?
So yes, that's implicit in this proof actually. In this proof, actually what it does is it constructs the correct it constructs the clique from the assignment and also the assignment from the clique. Yeah, and that's what we would do for other proofs as well. But I mean, yeah, here in the top level statement, I kind of just quantify out that encoding. Yes. Yeah. So and of course what you can do is then plug it into the proof checker. For example, I've skipped over this part, but you can show, for example, if the proof checker says that, well, your formula, it ran the proof and it checked that the final formula obtained was unsatisfiable, then indeed your input formula was unsatisfiable. So you can prove something like that, which I don't think the proof runs now because I sort of ran it halfway. Okay, so that's kind of what I mean by building a front end. And then I just wanted to quickly show the final theorem that you can build for one of these front end plus back end combinations. So this is actually the proof checker for cake PB click, which is the cake PB with a click front end. And what it says, this is the standard theorem that's generated for cake ML proof checkers. And what it says is that if you manage to successfully run the cake PB click on a certain command line with a certain file system setup and on a certain machine with under the standard assumptions, then you guarantee that the machine code semantics, which according to our formalization is such that the click proof checker will always sort of print something out unless it runs out of memory. And in particular, it prints an output and error string. And sorry, it prints the string to standard output and string to standard error. Okay. And if the standard output was non-empty, then you're guaranteed, for example, in the case where you have passed the proof into the checker as well, then you're guaranteed that output is bound on, in this case, for example, the max click size of the graph. Okay. And one thing to note about this, for example, is that this proof checker talks directly about the mathematical semantics of what it means for a graph to have a click. Okay. So it doesn't, for example, need to even mention the intermediate pseudo-Boolean semantics, which is used in the proof. Okay. Right. So I am happy to dig into this further separately. Yeah, and I just wanted to kind of summarize, which is that I would say, yeah, spending quite a bit of time. I mean, it does require a little bit of effort to get started, but we're very happy to help if anyone wants to build a new verified front end encoder. If anyone wants to come in and help with improving the backend performance in terms of improving and verifying the code. And in particular, if you want to do it yourself, you're happy to get you started as well. So thank you for your time and attention.
More questions for Yong Kiam?
I'll how bad would it be to add a new rule into the CakeBB format? For example, the meerkat.
So that I would say that is actually not difficult. So it depends on how much the new rule has to change the invariance of the system. So if you don't have to change the invariance of the system, then what you essentially need to do is, in terms of this script, is to do step 1 for that particular rule. So you would define, right? You define something about the meerkat. You define how to actually run the meerkat. Then you would prove the soundness of, let's say, so given a constraint C, applying the meerkat with, I guess, a divisor D, you would show this kind of correctness theorem for it, right? And then what you would do is you add it to the top, to the, I think, the cutting planes checker, okay? And I guess I would say the rest of it, in the case of meerkat, would be more or less mechanical. But there are rules that would be a little bit more exciting to add, I would say. So I think one of the rules that we had talked about was this opt-I rule. And that one would require changing some of the soundness invariance around the checker. So that would be more work, okay? And then so that's an increasing order of effort. And then a third, sort of even more, the third thing that requires even more effort would be to, I would say, if you want to introduce a rule that requires one of these more detailed implementations, like, it requires some kind of optimized implementation. And one example of this would be, for example, when we introduced RUP. So we needed to actually make the RUP check pretty efficient. And then that would require actually working on step 5, which is actually improving the refinement and doing the refinement more carefully than just doing this translation. Yeah. So I would say the answer is really, it depends on what rule you're adding.
Okay, thank you.
More questions? Otherwise, let us thank Yong Kiam.
Okay, thanks for your attention. I'm sorry for going over time. To the next speaker. Hope you have the nice rest of the session. See you.